pressure variation in a fluid at rest. Now, let us consider a small element ABCD. Let us consider a small element ABCD as shown in your figure. You can see a small element ABCD in the figure. There, let delta A, let delta A be the cross-sectional area of this element. Let delta A be the cross-sectional area of this element A, B, C, D. And let delta Z be the height of the fluid element. Let delta Z be the height of the fluid element. Now let us assume small p as the pressure acting on face AB. Small p as the pressure acting on face AB. Delta A is the area assumed, delta Z is the height of the fluid assumed, and P is the pressure on face AB. Small p is the pressure on face AB. And Z is the distance of this fluid element from the free water surface. Z means it is the distance of the fluid element from the free water surface. Now we have to consider all the forces acting on this fluid element. You know, force equals pressure into area. Force is equal to pressure into area. Now, what are the forces acting on this fluid element? First one will be pressure force on AB. Pressure force on AB. The pressure on face AB is small p and the area assumed is delta A. Therefore, the pressure force on AB will be P into delta A because force is equal to pressure into area. So, the force on AB is equal to P into delta A, which will be acting in a downward direction. You can see this is acting in a downward direction. Next, you can see pressure on face CD. There, the pressure is P plus dou P by dou Z into delta Z. So, firstly, we consider the force on AB. Next, we have to consider the force on CD. So, force on CD will be equal to pressure into area. Then the pressure on face CD is P plus dou P by dou Z into delta Z. And the area is delta A. So, the pressure force will be P plus dou P by dou Z delta Z into delta A. And this force is acting in an upward direction. Now we found two forces. One is the force acting on face AB and next is that acting on CD. Then you should remind that force is equal to pressure into area. So on face AB it becomes P into delta A because we assumed the pressure on face AB as small p. Okay, now we consider two forces, that is on face AB as well as on face CD. Now we have to consider one more force, that is the weight of the fluid element. The third force is weight of fluid element. So you see, first is a pressure force on AB, second is pressure force on CD, and third is weight of fluid element. So weight can be represented as mg. You know W is equal to mg. So we may write it as density into G into volume because density is equal to mass by volume. So that denominator will get cancelled with this volume. Volume and volume will get cancelled. So the remaining term will be m into G. W equal to mg എന്ന് പറയുന്ന ഇതിനെ മറ്റൊരു ഫോമിൽ എഴുതിയേക്കാണ്. Weight is equal to density into G into volume. കാരണം density is equal to mass by volume. So volume and volume will get cancelled. So the remaining term is mg. So instead of writing W is equal to mg, we are just writing weight of fluid element is equal to density into G into volume. Then what is density? Rho. And what is volume here? You know, delta A is the area and delta Z is the height of fluid element. So what will be volume? Delta A into delta Z. So the weight of the fluid element will be rho into G into delta A delta Z. Now, for equilibrium of fluid element, we may write P into delta A minus P plus dou P by dou Z delta Z into delta A plus rho G delta A delta Z is equal to 0. The first term is the pressure force on AB. Second term is the pressure force on CD. And third term is the weight of fluid element. You know, the first force, the first term, that is P delta A, that is a force on AB, is acting in a downward direction. Similarly, weight is also acting in downward direction. So, first term and third term will have same sign. And the second term is the force acting on CD. So, since we are considering downward force as positive, the upward force will be negative. So the first term and third term remains positive and second term remains negative because we have to consider the direction of force. On face AB, the force is acting downward, while on face CD, the force is acting upward. You open the bracket, then you can see P delta A minus P delta A minus dou P by dou Z delta Z plus rho G delta Z is equal to 0. Now you know P delta A and P delta A get cancelled. Now the remaining terms are dou P by dou Z delta Z is equal to rho into G into delta Z. Again you can see delta Z get cancelled. So you may write dou P by dou Z is equal to rho G. Assign it as equation 1. Then what is rho G? In fluid properties, you have learned that rho G is equals W. So you may write rho G equal to W. Therefore, equation 1 become dou P by dou Z is equal to W. Where W is the weight density of fluid. You know W is equal to weight density of fluid, that is equal to rho G. Now, from that equation, we can conclude that the rate of increase in pressure, in a vertical direction is equal to the weight density of that fluid. You can see the remaining term is W. W is the weight density of fluid. Therefore, we can write the rate of increase in pressure. The rate of increase in pressure equals the weight density. So, we have finally concluded that the rate of increase in pressure equals weight density. And this particular law is known as hydrostatic law. Hydrostatic law states that the rate of increase of pressure in a vertical direction equals the weight density of fluid, that is W, weight density of fluid at that point. This is known as hydrostatic law. Now, You integrate equation 1. Now, which is equation 1? You have marked already equation 1, that is dou P by dou Z is equal to rho G. Now, you just integrate equation 1. So, it will be integral dou P is equal to integral of dou Z into rho into G. You can see the integration here. That is integral dou P is equal to integral of dou Z rho G. From that, what is P? P is equal to rho into G into Z. Because rho and G are constants here. So, P is equal to rho G Z. That's our final equation. Pressure is equal to rho G Z. Z is the depth here. So, P is equal to rho G Z. If H is the depth here, P is equal to rho G H. Z means it is a depth of fluid. So, if H is the depth of fluid, what will happen? We may write P is equal to rho G H. So, we can write H or Z as P by rho G. And we may call Z as pressure head. So, once more, P is equal to rho G Z, where Z is the height of fluid element. But if we are assuming H as height of fluid element, P will be rho G H. That is the derivation. Okay. Thank you.